So in this lesson, we're going to take a look at vectors. We'll go ahead and we'll start here with a vector that looks something like this, with a point down here A and a point here, we'll say B. Now vectors have two characteristics. Vector will have both magnitude, which is just another name for length, and it will also have a direction. The direction now comes into play with the A and the B. You can see the direction arrow on this vector, which would imply A is the initial point and B is the terminal point. And this vector then would be represented by the notation AB with the vector bar on top. So an initial point, a terminal point, that helps us with direction, and then the magnitude would be the overall length. Now the AB, the notation you'll see pretty commonly. You'll also see us commonly say that this is vector V or W or whatever. In most textbooks though, there'll be bold letters, and so when you're reading your text you'll see bold letters, and those denote the vectors. So now we'll go ahead and we'll talk about the operations with vectors geometrically, and we'll start with scalar multiplication. So I'll go ahead and I'll draw a vector V, and a scalar, as we know, is just a real number. So for example, if I took the vector and I multiplied it by 2, it would still have the same direction, but it would be double its original length. Similarly, I could go ahead and I can multiply the original by a 1/2, which means it'll be half the length of the original vector. And then if I ever wanted to change directions, I could use a negative V, and it would be the same length as the original, but it would point now in the opposite direction. So a really important property of vectors and scalar multiplication is that the vectors, as you can see in the picture, as long as they're scalar multiples of one another, they're going to be parallel. So vectors are parallel if and only if they're scalar multiples of one another. So now we're ready to talk about vector addition and subtraction, again geometrically. So we'll go ahead and we'll start here with a vector V, and then I'll also construct now a vector W. And I've positioned these in such a way that their initial points are touching at the same place. So what I'll go ahead and do now is I'll extend this guy out, I'll extend this out, and I'll extend this up. And what I'm doing is actually creating a parallelogram. And the resultant vector coming out of the point where their initial points are together, that's going to be the sum of V plus W. This is referred to as the parallelogram law for vectors. So the blue vector is V plus W, also known as the resultant vector. Now, in terms of subtraction, I just want to point out before I draw the picture that if I were to give you, let's say 5 minus 3, that's the same thing as 5 plus a negative 3. So I'm essentially going to put together the sum of two vectors again, but one of the vectors now will have a negative scalar. So I'll go ahead and I'll move the other direction with this. So here, we'll go ahead and we'll call this negative V. So it's the same vector as V, but now it points in the other direction. And from here, we can also again construct this parallelogram. And coming out of where the initial points are together, this would now be your resultant vector. And so we would really have W plus a negative V, which is also W minus V, and there's your subtraction of two vectors. So now, before we transition to vector operations algebraically, we need to talk about component form of vectors. Now, before we really get into even the component form, we need to talk about vectors in standard position. Now, a vector in standard position is just a vector now with its initial point at the origin. So if that's the initial point, there would be a vector in standard position. Now, because of how we know vectors work, the terminal point here would be the point x, y, which means that point was found by moving right a distance of x and up a distance of y. So we've got a point, the terminal point is the point x, y. And so if we view this now as vector v, then vector v can be written in component form as x, y. So again, notice the notation where this is a point and this is a vector. We have the different notation here on a vector versus a point. Now, a couple other things that we could point out in a picture like this. You could see that maybe I'll call this guy theta. And now we've got a right triangle here, and we can apply a lot of our trigonometric ideas to the vector itself. For example, I know that to find theta, I can use y over x. And remember, the y and the x would be given or be part of this problem because that's part of the vector. And if I ever wanted to figure out the magnitude of v, then notice the notation on magnitude. For the magnitude of v, that would just be the square root of x squared plus y squared. So for the two characteristics vectors, you've got direction and you've got magnitude being able to be computed now in a very easy way since the vector is in standard position. So in this first example here, we're told to find the magnitude and the direction. And so a pretty straightforward problem. If this guy is vector v, the magnitude of v would be the square root of -4 squared plus a -2 squared. And if I simplify this, this will be a square root of 16 plus 4, which is the square root of 20, which would be the 2 root 5. So the magnitude of that vector would be 2 square root of 5. Now, for the angle, we would have our y value, which is -2, over our x value of -4, which gives us a 1/2. So we would want to follow this similar to how we've done in the past, where we say tangent is positive in quadrants 1 and 3. So tangent's positive in quadrant 1, tangent's positive in quadrant 3. Now, to decide which one we want, we're going to need to go back and look at the original. Now, the vector is -4, -2, but if you remember, the terminal point would be -4, -2, which would be clearly the triangle in quadrant 3 that we're interested in. Now, the 1/2 here, this is not one of our special triangles. So for us, it's going to be a matter of determining that theta is the inverse tan of 1/2, but understanding that our calculator would give us the angle in quadrant 1. So for us, we're going to need to take 180 degrees plus the inverse tan at 1/2, of course, in degree mode. And in doing this, we find out that theta ends up equaling 206.6 degrees. So that's your direction angle, and there sits your magnitude. All right, so in this example, we're now going to be given the magnitude and the direction vector, and it's up to us to come up with the component form. Now, before we do this, I'm going to redraw the picture I had just a moment ago where we said, okay, if this is vector v, then we'll call this guy maybe x, and we'll call this guy y, and that was a theta. Let's go ahead and take a look at, again, some just basic observations. I know that cosine of theta would be the x over, not the v, but the magnitude of v. And I know that sine of theta would be y over the magnitude of v. So if it's my job to find the terminal point, which in turn we could rewrite now in its component form, then I can say x is going to be the magnitude of v cosine theta, and y equals the magnitude of v sine theta. So really I'm just plugging stuff in at this point. The magnitude would be 5.3, cosine of 321 degrees, and once again 5.3, but now sine of 321 degrees. And when we punch this in a calculator, we find out that x equals 4.1, y equals -3.3. So then vector v in component form would be 4.1, -3.3. So again, some basic trigonometry now that we're able to write these vectors in standard position.